We're talking about vertical asymptotes for rational functions. So as the name implies, a vertical asymptote is a vertical line that the graph of our rational function is approaching. And actually finding vertical asymptotes is fairly easy. All we have to do is to find what is it that would make the denominator of a rational function 0. So to find the vertical asymptote, and it could be more than one, set the denominator equal to 0 itself. Let's have a few examples. Let's go to the next page. Suppose I have something as easy as f of x equals 1 over x. Well, I know that x cannot be 0, so we have a vertical asymptote at x equals 0. Okay, let's do another one. How about if we have something like some g of x equals 3x plus 1 over x to the second plus x. Okay, so I'm going to go ahead and set the denominator equal to 0. X squared plus x equals 0. Let's factor an x out from left-hand side. So I have x times x plus 1 equals 0. So x equals 0 and x equals -1. Using, let me just actually write here, using 0 product property, I set both factors equal to 0, x equals 0 and x plus 1 equals 0. So the second part gives me x equals -1. So I do have two vertical asymptotes at 0 and -1. So vertical asymptotes at x equals 0 and x equals -1. Okay. And you can always test it. If I plug in 0 in here, 0 squared plus 0 is 0. Can't have that. And if I plug in -1 in here, -1 squared is +1 plus -1 gives me 0 again. Let's do another example. Let's say that find the vertical asymptotes, and of course I should put in parentheses if any, for the rational function g of x equal 2x minus 1 over x plus 1, x plus 3, and let's say x minus 4. Well, in this case, the denominator is already factored for me, so I don't have to do lots of work. And so here, again, using 0 product property, I'm going to set the denominator x plus 1 equals 0, x plus 3 equals 0, and x minus 4 equals 0. This one gives me x equals -1, x equals -3, and x equals +4. So vertical asymptotes at x equal, let's start with the smallest, -3, -1, and then 4. All right, let's see. How about if I had something like f of x equals x plus 1 over x squared minus 16. Please realize or notice that when I set the denominator equals 16, x squared minus 16 equals 0, I have two things I can do. I can say this is x plus 4, x minus 4 equals 0. And then x equals -4 and x equals +4. Or you could say x squared equals, add 16 to both sides, and x equals plus and minus 4, taking square root of both sides. Either way. So the vertical asymptotes at x equals -4 and x equals +4, we have vertical asymptotes. So the natural question here is to ask, what if a factor in the numerator cancels one of the factors in the denominator? Then what? Suppose if I have g of x equals x plus 5 over x to the second minus 25. Well, if I factor the denominator, then I have x plus 5 over x plus 5, x minus 5, difference of two squares. And notice that this is the same as saying 1 over x minus 5. And, I mean, if I look at here and ask myself, what would make this 0? I know that at x equals 5, this is 0, x squared minus 25. And at x equals -5, x squared minus 25 equals 0. But when I simplify my rational function and look at the end result in here, I only have 1 over x minus 5. And here at x equals +5, I have the denominator 0. So what happens in here? Well, it is true that both +5 and -5 make the denominator of g of x 0. But here we have to remember that the g of x was not on its most reduced form. So it wasn't the proper rational function. So the answer is for this one is only at x equals 5, we have a vertical asymptote. So does +5 do anything to the graph of g of x? And the answer is yes. There is a discontinuity at x equals 5 if you graph g of x. But that discontinuity is so very small, it is impossible to see it in the calculator or even a huge screen. So we do show that when we graph things by hand, we show that. So let's say that it would be something like this. So let's say that the graph continues and there's a little hole there at x equals 5, and then the graph continues. Okay, let's do one more. How about this time h of x equal x plus 5 over x squared plus 7x plus 10. And notice that this, once again, our rational function is not on its most reduced form. So it's not a proper rational function, it's improper. This is x squared. Okay, let me My handwriting is not so good, I'm sorry. So in fact, h of x equals x plus 5 over x plus 2 times x plus 5. I factor that. And now that equals 1 over canceling x plus 5 from numerator and the denominator. I have x plus 2. So what can I say about this, the graph of this rational function? I have a vertical asymptote at x equals -2. Why -2? Because -2 would make the denominator 0. And I can say that I have a discontinuity at x equals -5. Because x equals -5 makes both the denominator and numerator 0 at the same time. And as I showed, I could cancel that. One last note is that if you graph h of x from the here or from the reduced part, the graphs are identical. If you use calculator, and if you use even decimals, a huge screen, even if you have a really, really big screen as big as stadium, you still will not be able to see that discontinuity by eyes because x is getting really, 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 really close to -5, from both sides, from left side and from the right side, but it will not be exactly equaling -5. Okay, I'll do more video for you soon. Thank you.